Lab 4 Oscillations, presented by Andrea Otero. The purpose for experiment number 4 was to model the movement of an oscillating spring mass system that to some extent contains some of the behaviors in extreme sports. In order to do so, a model based on Newton's second law that predicts the motion of a mass attached to a spring was constructed in Python. In the Python model, we also computed the energy principle to see whether the model satisfied it or not, which it did. Finally, the Python model was also able to compare the modeled motion of the spring mass system compared to the analyzed data extracted from Tracker. Using Tracker, we were able to analyze the action motion of a spring that oscillated up and down and moved from side to side. As we can see in the picture, Tracker was able to extract the x and y positions of the mass attached to the string over time and was able to graph it. Using Newton's second law, we were able to construct our first Python model, which predicted and modeled the movement of an oscillated spring. We considered the mass of the spring as our system, where gravity and the spring forces were the only forces acting on the system. Initial conditions such as the mass of the ball, which was 0.402 kilograms, the ball's initial position, which was negative 0.117 in the x, negative 0.625 in the y, and 0 in the c meters, and an initial velocity of 0 were plugged into the Python model. Calculations were made in order to calculate the constant k and the relaxed length LO of the spring in order to be able to calculate the spring force. In order to do so, calculations as the ones showed on the video were made. Afterwards, the calculations previously made and the interaction initializations were defined in the model, such as g, the spring constant, the relaxed length, the total length, and the displacement s. Finally, we were able to compute the gravitational force, the spring force, and the net force acting on the system, on the mass, in order to apply Newton's second law to predict the motion of the oscillating spring. Our first model illustrates with the black arrow the weight force, or the gravitational force, and with the blue arrow the spring force. The graph illustrates with the blue line the movement of the spring in the y direction. The Python model was then edited and the energy principle was applied in it, in order to graph the different energies that were interacting in our system. In this case, however, in order to be able to apply the energy principle correctly, we had to choose the mass, the spring, and the earth all together as part of our new system, in order for the change in energy to be equal to 0, since there will be no energy or forces transferred to or from the surroundings with the system chosen. The energies identified were the kinetic energy, the gravitational potential energy, and the spring potential energy, which were plugged into our Python model. Finally, as the graph shows, the Python model computed a graph showing the changes in the energies, with the blue line representing the change in the kinetic energy. The green line shows the change in the gravitational potential energy. The red line shows the change in the potential spring energy. And finally, the yellow line shows the total energy change in our system. Finally, we were able to graph the computer model and the real movement with the data extracted from Tracker and construct a graph that compared both results of the movement in the y-axis of the oscillating spring. As the graph shows, the blue line represents the predicted motion by the Python model constructed, and the red line represents the real movement from the data extracted from Tracker. We can therefore conclude that our model was fairly accurate, since there were small discrepancies between the two graphs. For the analysis, we can then conclude that, as shown before, the energy principle is satisfied for the model system constructed in Python, because as the graph showed, the change in energy was equal to 0, represented by the yellow line, meaning that the energy was conserved. Even though the different energies graphs look asymmetric, they still add up to 0. Therefore, they satisfy the principle. As when comparing the periods from the y and the x movement of the spring, we can conclude that they were slightly different, and the period in the x position was smaller as shown in the graph and the values calculated. Such can also be seen by analyzing the graphs created by the extracted data from the real video in Tracker that shows the movement in the y and x position respectively. We can conclude that we use the period from the y position because the forces acting on the mass on the spring all act significantly on the y position, and the movement in the y position is more spring-like. On the other hand, the x movement was more pendulum-like. Thank you for your time.